Okay, so today we're going to go over some practice questions for exam 3. Remember, these are practice questions. They are not necessarily exactly like what's going to be on the exam, but they do test the concepts in a similar way that we might ask things on the exam. So this should be good practice. Keep in mind, on this exam, you're going to get a few constants. You're going to get Planck's constant, you're going to get the speed of light, and you're going to get the Rydberg constant. You're also going to get some equations. You're going to get the Rydberg equation, E is equal to RH over n squared. So this is the Rydberg constant divided by the energy level squared. Now, you will have to know how to do the derivations with this, though. That's a fundamental concept in terms of working with the energy and with Rydberg, with the energy levels. So that's something that you're going to have to remember, and if you look back at the video from that chapter, I go over how to do all of that. So that was on the video lesson that we had. Now the other one you're going to get is lambda equals Planck's constant over mass times velocity. This is the de Broglie equation. As you'll see, we don't do very much with that, but you should be prepared. I don't believe there are any questions on this practice exam, but you might get a simple multiple choice question related to the de Broglie wavelength. So do be prepared to do simple calculations with this, meaning to understand the relationships. But other than that, we don't do very much with it. So you should know how to use it, what it's all about, but we don't do very much with it. Okay, so let's jump in with the first multiple choice question. So on this exam, because it's so conceptual, we're going to have a bunch of multiple choice questions, but probably about 5 to 10, somewhere in there, depending on how things go. But generally speaking, this is a good way to test some concepts. So with the first one, this one asks, according to the building up principle or the off-Bohr principle, which subshell is typically filled next after the 3D? So if you go through, this is pretty straightforward. You just follow it along. So it's going to be, you have 1s2, 2s2, 2p6. I'm just going through my periodic table. Then we're going to go down to 3s2, so this brings us up to magnesium. I'm sorry. This brings us up to magnesium here, the configuration for magnesium. 3s2. Then we get 3p6. That's going to bring us up to argon. And then we drop down and we get our 4s2. Then we get our 3d10, so now we're up to zinc. And then right here is what it's asking us, so what comes next, and this would be the 4p's. So that's what's next if you follow the building up principle. So the correct answer here would be A, 4p. Okay, so which atom has the lowest ionization energy? Remember, the trends for ionization energy are that ionization energy decreases, because we're interested in low. So what is the lowest ionization energy? So the ionization energy decreases as you go down in the periodic table or as you go to the left of the periodic table. The idea being that as you go to the left, these ones have the least effective nuclear charge, so it's easiest to pull an electron away. And the same thing as you go down, as you add more shielding subshells in between, it gets easier and easier to pull that electron away. So if you look at the list, silicon, let's get this here. So we have silicon, carbon, these are all pretty high up. Tin goes down a little bit, so we're going down. We have lead, that's even further down, and then we have germanium. So this is basically just going down a row, a column, and so this will be the lowest one, which is just lead. So the correct answer there would be E. So the next one is, which one has the smallest atomic radius? So again, if we look at atomic radius, the atomic radius is going to follow the trend of effective nuclear charge. So it's basically, as the effective nuclear charge goes up, the nucleus is more effective at pulling the electrons in. So what that means is that as effective nuclear charge increases, your atom's going to get smaller and smaller and smaller. So we're going to look for something that is high and to the right here. So we have chlorine, which is here. We have rubidium, that's lower than chlorine, so we can get rid of that one. Calcium is lower than chlorine, so we can get rid of that one. Silicon is to the left of chlorine, so that is going to have a less effective nuclear charge, so still we're set on chlorine. And then there's arsenic, which is below, so the only choice here would be chlorine. So the correct answer is going to be A for that one. So going along, we have which has the highest electron affinity. Just looking at this one, I can see already it's probably going to be chlorine, because that one definitely is highest and to the right, just looking at the elements, but we can track that out. So electron affinity, we did not go over in class what happens as you go down a row, so you're pretty much looking for things that are to the right of the periodic table. So we can basically get rid of rubidium right away. Arsenic is to the left of chlorine, so that's not going to be the case. And then selenium is also to the left of chlorine, so it comes down to chlorine and bromine. And in this case, chlorine has the highest electron affinity. We know that because chlorine becomes a negative ion more favorably than bromine does. So in this case, there is a slight increase as you go up the row for chlorine. So that would definitely be the best case. The best answer would be chlorine in this case. So that's C. The next one is a very interesting question. So this one goes to the understanding of, or the combination of what is going on between electron configurations, the octet rule, and ions. So it is a little hard to see this. I'm going to zoom in just a little bit so that you can see the ions in this case. So in this case, it asks us, atoms of an element X have a ground state configuration of 3p4. Just to put us on the map, 3p4 is going to be, 3p4 is going to put us in the area of sulfur. So the question is what type of ion is X most likely to form? So when an atom forms an ion, that ion is going to want to have an octet, meaning that it's going to want to have a full shell. So for elements that are on the left of the periodic table, like sodium and magnesium, those ones are going to want to lose 2 electrons and form a positive. Ones that are on the right, or the main group elements, those are going to want to gain electrons. And in this case, for this guy to gain an octet, so to go to 3p6, we're going to have to add 2 electrons. So plus 2 electrons. So that means that the only possible case is going to be X2 minus, because if you think about it, the configuration for that is going to be this plus 2 electrons, which is going to be 3p6. So the correct answer here is going to be D. So the X2 minus, and the way that we know that is because sulfur and oxygen, which is what these electron configurations, those ones on the periodic table tend to form minus 2 charges. So that's just something you can know from the end of chapter 7. So question number 6 is related to the Bohr-Haber cycle, which is basically your lattice energy type questions. Now, the reason why we like to ask this in a more conceptual form rather than in a more numerical form is because it's very difficult in the short period of time you have to take the test to do a lot of numerical equations. You should be prepared to do a numerical calculation, but also be very prepared to do conceptual type questions like this. So this guy asks us, which one of the following processes is exothermic? So this is something that you're going to have to remember back to the lecture notes. We went over this in detail when we talked about the Bohr-Haber cycle. We did cover which steps were exothermic and which steps were endothermic. So, I mean, just to kind of go through again, pulling an electron away. So this is the first ionization energy right here of cesium. So pulling an electron away, whenever you pull an electron away, you have to break the positive-negative interaction. So that automatically is going to be something that's going to require energy and be endothermic. Here you can see this is the lattice energy, which is B. So we're basically pulling apart positive and negative ions to form these ions in gas phase. That is pretty obviously going to be an endothermic process because you have to pull apart the ions. Here we have the electron affinity. Actually, this is the inverse of the electron affinity. The true electron affinity is F minus goes to F gas plus 1 electron. So this process, the way it's written, whenever you give an electron to an atom, that's going to be an exothermic process, with the exception of basically just the noble gases. So in this case, the answer I can tell you already is going to be C, but we'll keep going. So going from cesium solid to cesium gas, this is a sublimation. Whenever you go from either a solid to a liquid or a solid to a gas, you're going to have to put in energy to overcome the intermolecular interactions. And then here we're breaking a bond. We're going from fluorine, molecular fluorine F2, which is basically FF to F and F. So we've broken the fluorine-fluorine bond. So that's going to be an endothermic process. So the only correct answer here is C. One of my favorites. So this one is challenging because you're going to have to write 5 different Lewis structures to figure out the question. So for those of you who thought that multiple choice were going to be easy, they are not so easy necessarily. So in this case, we have which one of the following Lewis structures is the most similar to NO minus. So the first thing we have to do is write the Lewis structure for NO minus. So N brings 5 electrons to the party, O brings 6, and then we have 1 for the minus charge, so that's going to give us 12 electrons. So with 12 electrons, we write our skeletal structure. So this is going to take away 2 electrons for the bond, so that leaves us with 10. So if we put our 10 in, 1, 2, 3, 4, 5, this is going to give us this structure. So we know that we have to satisfy our octet for the NO. We have to satisfy our octet for the nitrogen. So in this case, we're going to have to slide one into the middle. So the best structure is going to be N double bond O with 2 lone pairs on the end. And if you count formal charges, this guy is going to be 5 minus 4 from the lone pairs minus 2 is going to give you your -1. That explains the -1 charge. And here, this is going to be 6 minus 4 minus 2. 6 minus 4 minus 2, and that's going to be equal to 0. In this case, there's no other way to write this structure, so it becomes basically this. Now, you would have to probably go through on the exam and look at all of the structures, but if you look, this basically has 2 lone pairs on either side and a double bond in the middle. I can tell you already that that's going to be the structure for O2 gas. If you do it out here for O2 gas, there's going to be 12 electrons for each atom. So already this is a way that you can tell. These are all binary pairs, right? So I'm kind of showing you a way to save time, how I can tell right away. It's a binary pair. So the only way that you're going to get the same electron configuration, the same Lewis structure configuration, is if you have a binary pair with the same number of electrons, right? Because they're going to distribute the same way if you have the same number of electrons for the same number of atoms, generally speaking. I mean, you should, on the exam, do all of them out, just to make sure, or at least do the one that you think, try it the way I'm suggesting it. So the way that I went about this was to say, well, what's the one with the same number of electrons? And the only other one with the same number of electrons is O2. O2 minus, this is going to have 13 electrons. O2 2 minus is going to have 14 electrons. O2 is going to have 12. NO is going to have 11. And then NO plus is going to have 10. So pretty much doing this right away, you can see that the O2 is going to be the best case. But anyway, let's do it out just so that we can do it. So we have the OO bond, so we're going to take away 2. We're going to have 10 electrons there. If we distribute these 10 electrons, that's going to be 1, 2, 3, 4, 5. And just like we did with the nitrogen, that's going to give us O double bond with 2 lone pairs. So in this case, the correct answer is going to be C. My recommendation is that you use that process that I used, that I just showed you right there, which is to look for species with similar bonding pairs. Look for species that have similar numbers of electrons to be distributed, because generally that's going to give you the best answer. But if you have to, just do them all out. It doesn't take that long to write the Lewis structures, and then that way you can definitely know that you got the right answer. You can always, another way to do it is you can always come back and look to see. So you kind of do it my way, and then you can go back if you have extra time and double check. All right. So the next question on the exam is we're now moving into the open-ended questions. Here's a straightforward Bohr model calculation where it wants to know the wavelength and the frequency. Now on the exam we wouldn't ever ask you for both. We would ask you for only one, but here I asked you for both so that you can go through the process of practicing doing both, and I will show you how to do both. And then it says from a hydrogen atom. That's important to remember, because on the exam the Bohr model only works for the hydrogen atom or any atom that has 1 electron. So you should be prepared to potentially do this for a helium plus atom, for a lithium 2+ atom, so on and so forth. But basically, this is going to work for the hydrogen atom because it has 1 electron. So calculate the wavelength and frequency of light emitted. So the energy in this case is, we're going to go to our Rydberg equation. Energy is going to equal the Rydberg constant times 1 over n final minus 1 over n initial, and these terms are squared. And so the energy is where you can plug in whatever you need. So keep in mind that energy of a photon, so this is going to be energy of a photon. So basically, whenever you get a transition from one state to another, from one energy level to another, that's going to correspond to either a photon that's absorbed or a photon that's emitted. So the energy of a photon, we're going to use Planck's equation, is going to be Planck's constant times the frequency. So we can plug this guy in on this side. H times the frequency is going to equal 1 over nf squared minus 1 over ni squared. And just to make our life easier, I'm going to write the following, where I move that h down below, and I take this as 1 over nf squared minus 1 over ni squared. Okay. So this is going to give me the answer in terms of the frequency, so I can plug everything in. So the Rydberg constant is, I might have to look that up, but the Rydberg constant is 2.179, I don't have to look it up, I remember it, times 10 to the minus 18th joules. And Planck's constant is 6.626 times 10 to the minus 34th joules per second. You'll notice that the joules cancel out, giving you the per second. And then on this side, we are going to have our 1 over n final. So n final in this case is going to be, our n is equal to 2. That's where the electron winds up. So that's going to be 1 over 2 squared minus 1 over 3 squared, which is where it started. So let me grab my calculator, which is here. I'm going to plug this all in so that you can see it. So 2.179 times 10 to the minus 18th divided by 6.626 times 10 to the minus 34. That's going to give me 3.28 times 10 to the 15th for the frequency factor, which is basically these terms here. And then we will multiply this by 1 divided by 2 squared minus 1 divided by 3 squared. And the order of operations in the calculator should work here. The subtraction will go last. Both of these will get squared first because it's, remember, PEMDAS, and then it'll do the division. So this should all work out correctly. and we get the answer, which is 4.57. So the frequency that I calculate is 4.57 times 10 to the 14th. So let me write that down here. Frequency equals 4.57 times 10 to the 14th 1 over seconds. So I can box that off. That's part 1. And then in this case, you can convert this to the wavelength, since I asked you for both, which is C equals lambda times the frequency. So the frequency in this case is going to be the wavelength in this case is going to be C over the frequency. So we have 3.00 times 10 to the 8th meters per second divided by the frequency, which was 4.57 times 10 to the 14th 1 over seconds. So my seconds will cancel, leaving me with the units of meters. So if we do the calculation here, we get 3 e to the 8th divided by 4.57 e to the 14th times 10 to the 14th. So we get a wavelength of 6.56 times 10 to the minus 7th meters. So this would be the wavelength and this would be the frequency. Now be prepared on the exam, you may have to convert this to nanometers or work with this in nanometers. So now in this particular question I didn't specify. So a couple of things about this question that I want to point out. Number one, with this, the sig figs are sort of irrelevant because there's really nothing that's defining the significant figures. The 2 and the 3 are absolute numbers, and these guys have way more significant figures than I wrote. So if you choose 2 or 3 significant figures, that's fine. I'm really not grading on significant figures. Just make sure you choose like 2 or 3, a reasonable number. 2 or 3 is good for this. So that's one thing that I wanted to point out. The other thing that I wanted to point out is that these constants will be given to you on the exam with the units. So you don't have to memorize them, but you do have to know, generally speaking, like that I showed you the canceling of the units and all that stuff, that we can't give that to you on the exam because you have to know how to do that. But I'm just going to flip this guy around. So our wavelength in this case was 6.56 times 10 to the minus 7th meters. Now, it is very possible and very probable that I will give you some kind of conversion to nanometers as an extra step. Most likely, you'll get. I'll either ask you to calculate the wavelength in that and calculate the wavelength and give the answer to me in nanometers, or I will give you a wavelength in nanometers and tell you to calculate tell you to calculate one of the transitions. So which end did it start with or something like that. So just keep in mind that when you're doing these conversions, that there is, for every 1 meter, there is 1 times 10 to the 9th nanometers, okay? So this is the conversion that's very relevant to this type of question, and you should keep this in mind. And not surprisingly, we are going to get, if we do this math, if we multiply this by 10 to the 9th, we are going to get something like 656 nanometers, which is very much in the visible range. And this is exactly what you would expect because the transition of hydrogen are in the visible range. So I just want you to consider that because, these transitions that we get are things that you can actually see with your eyes. Okay, so that sort of takes care of this question. I just wanted to point it out, that one thing. As we're going. Okay, so now we're going to do some electron configurations. These are some good representative examples of different ones that you might want to do. There's some ions in here. There's some main group elements, some metalloids like aluminum, some metals like aluminum, and some metalloids like selenium. So what this guy wants is an electron configuration, a valence orbital diagram, and whether or not it's paramagnetic. So for aluminum, this is going to be, so if you grab your periodic table and you go across, you're going to have 1s2, 2s2, and then for aluminum, you're going to get a 3p1. I'm sorry. I missed some things here. I got to cross this out. So you get 2s2, 2p6. That's going to take us over to... so let me cross that out. So you're going to get 2p6. That's going to take us over to neon. Then we're going to get 3s2. I jumped ahead a little bit. And then we're going to get 3p1. All right. So that's the correct electron configuration for aluminum. And then in here, the valence configuration is going to be... we're going to have our third subshell, so it's going to be a 3s. That's going to have 2 electrons. And then we're going to have the 3p, which is just going to have that 1 electron in the 3p1. So is this guy going to be paramagnetic? Yes, because it has 1 valence electron. So that's what we're looking for in this table. Most likely this table will appear on the exam. We pretty much always ask it. We just change up the elements. We ask for, either more or less difficult elements, and then there are some straightforward ones like aluminum, and then there'll be some more challenging ones like the ones that you'll see ahead. Now, for strontium, I'm vague here about the electron configuration. So typically, I personally will accept if you would like to either write the full electron configuration, or in the case of something like strontium where it's pretty far down, that's going to be in the 5th row. Let's see, 1, 2, 3, 4, 5. That's going to be in the 5th row. You can use a noble gas configuration to summarize. But ones that are short like this, you'll probably want to write them all out just so that you can cover all your bases. But for one like strontium, you can do it. Generally speaking, I do not mind if you use a core atom, as long as you get that core atom correct. Like I said in class, generally speaking, you can go either way. The only time you can't go either way is if I explicitly say complete electron configuration. If it says complete electron configuration, you can't use a noble gas core. If it just says electron configuration, or that you can use a noble gas core, then you're okay, you're fine. And almost 90% of the time, that's how it's going to be. So in this case, we're going to have a krypton nucleus. And then we're going to have let's see, 1, 2, 3, 4, 5s2. Now, if you wanted to write out the full one, I'm going to do that down here so that we can, so that you guys can just see what it would look like fully done, so that there's no questions about how we want this done on the exam. So in this case, this would be 1s2, 2s2, 2p6, 3s2. Then we're going to go to 3p6. Then we get to 4s2. Now, here's where we get to the 3d10. So we're just filling up with the Aufbau principle. We're going to do 4p6. Then we're going to get to 5s2. So that would have been the full electron configuration all the way out. Now, I would have happily accepted this on the exam, but since the box is kind of small, probably the noble metal core is the way that the noble gas core is the way you want to go. So here we just have a 5s orbital with 2 electrons in it. We have no unpaired electrons, which is the definition for diamagnetic. So in this case, this is going to get a diamagnetic. Okay, then we have selenium. So selenium is going to be a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then it's going to be the it is going to be the 3d10, and then it's going to be 4p 1, 2, 3, 4. So in this case, to show the valence electron configuration, we have to show the 4s, the 3d, and the 4p orbitals, and I don't have a lot of space, so I'm gonna kind of do this one out over here. If you need on the exam, we can give you, I can give you another sheet of paper or something to write this all out cleanly. We just give you these tables to make it easier to see what we're trying to get at. But we can open this up and you can use a separate sheet of paper. So in this case, we have the 4s, which is going to be completely full. We have the 3D, which is going to have 5 of these guys, 3, 4, 5. This is again going to be completely full. And then we're going to be left with the 4p. So this guy is going to have a 4p4 configuration. So this is going to be a up, 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 and then down, leaving us with 2 unpaired electrons. So this guy is going to be paramagnetic. Okay, copper plus. So this is a bit of a challenging one. So what I recommend that you do in this case is write out the electron configuration for the metal, the metallic form, and then once you have that, you can form the ion. So in this case, what we'll do is we'll do our 1s2, 2s2, 2p6, 3s2, 3p6. Then we have our now here's where it gets interesting. So copper is one of the ones that is a weird one. It is because the configuration, if you just followed the off-ball principle, would be the configuration would be 4s2 3d9, right? So 4s2 3d9, but it is not that. The metallic form is 3d10 4s1, okay? Because it is more energetically favorable to fill up the D and to have an unpaired electron in the 4s1. So this is one of those special exemptions. So when we make it the positive ion, this 4s1 is going to go away. So the correct answer is going to be that. So 3d10 is going to be your correct electron configuration. There is no more s, so all we have to do here is write 3d, 1, 2, 3, 4, 5, and we are going to have a completely filled 3d subshell, and this will be diamagnetic. There are no unpaired electrons. Okay, so the last one is iron 3 plus. So again, this one is a straightforward one when it comes to the metal configuration. So the electron configuration for iron alone, we'll flip over. So for iron is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then if you count over for iron, you're going to get 1, 2, 3, 4, 5, 6, 3d6, okay? So if we do iron plus 3, it's going to be all of the core electrons, and then we have to take away 3 valence electrons. Remember, these are the ones that go first, and then we have to take 1 from here, so that's going to leave us with 3d5, okay? So you take, for the 3 plus, you're going to take the 4s2 first, and then you're going to take the third one from the 3d. So when we write this, this is going to be 1s2, 2s2, 2p6, 3s2, 3p6, and then this is going to be 3d5. Okay? And here we're going to have the 3d, and then we put our 5 electrons in, following Hund's rule. We see we have 5 unpaired electrons, so this guy is going to be paramagnetic. Awesome. Okay, so that takes care of the electron configurations. I guarantee you there will be electron configurations on the exam. So you should really know how to do that. You should know how to make ions. You should know the exceptions. There are only two. The two exceptions are in the copper row and in the chromium row, where you have to promote one electron from the 4s to complete either the half subshell, the 3d5, or the 3d10. Okay, so the next one is related to bond energies and making and breaking bonds. So here, you just have to be able to draw out the Lewis structures for all of these guys. It's expected that you'll know simple Lewis structures like acetic acid, methanol, ethanol, things like that. Some simple hydrocarbons. We've covered all of that in nomenclature. We've covered a lot of that in lab. So those are things that you would have to know how to draw out. So methanol, the skeletal structure, and the reason why you need to know the skeletal structure is because we have to be able to count up the types of bonds. So this is the skeletal structure for CH3OH. We have the skeletal structure for O, which is going to be an OO double bond. CO2 is going to look like this. So you can draw the Lewis structures out for these if you need, but you should sort of get the feeling, you should get a feel for what's cooking here, what's going on. You definitely, this is going to be the kicker, so you're going to have to know simple hydrocarbons, methane, propane, ethane, things like that, methanol, ethanol, and acetic acid. So those are the common ones that you might see here. Those, we've all seen those in class a couple of times. We've seen them in lab a couple of times. Okay, so now what I like to do is to take my bond inventory. So in this case, we have a bunch of CH bonds. So we have 1, 2, 3 CH bonds, but because there's 2, we have to make sure that we get the fact that there's 6 of those. So we have 6 CH bonds here. We have a CO bond, so that there's going to be 2 of those because there's 2. The reason why I'm making this 2 is because there's 2 in the stoichiometry. So you have to make sure you take into consideration the stoichiometry. And then there's going to be an OH bond. Here, there's going to be 1 OH bond. So we're going to have 3 OO bonds. We're going to have, so in CO2 there are 2 CO double bonds. So in terms of CO double bonds, we're going to have 2 of them times 2 is 4. And then OH, we're going to have 4. And so for the OH bonds, we're going to have 4 of those times 2 in each one. That's going to be 8 of those. Okay, so now that we have our inventory, we can go to our equation. So we're going to sum up all of the bond energies on the reactant side, and then we're going to subtract that from all of the bond energies on the product side. So for a CH bond, it's going to be 6 times 411 kilojoules per mole. So that's 1. We're going to add to that 2 times our CO bond, which is going to be 358 kilojoules per mole. And we're going to have our OH bond, which is going to be 1, which is going to be, oh, I'm sorry, this should have been 2 because of the stoichiometry. This should be 2 times 459 kilojoules per mole. Okay, so we're going to do that all together. And then we're going to subtract that from that. We're going to subtract the reactant side. So on this side, oh, and I forgot, we also need to take into consideration our OO double bonds. So here we're also going to have to add 3 times 494 kilojoules per mole. Almost forgot. All right, so then on the product side, we have our 4 CO double bonds. So those are going to be 799 kilojoules per mole. And then we're going to add to that 8 times our OH bond, which is going to be 459 kilojoules per mole. Okay. So this is going to equal the delta H for the reaction. All right, so if we put this into our calculator, it's going to be 6 times 411 plus 2 times 358 plus 2 times 459 plus 3 times 494. Okay, and then we're going to subtract from that 4 times 799. Let me do this in parentheses so that it's easier for you guys to see. Plus 8 times 459. Okay, so we get a delta H is equal to minus 1,286 kilojoules for that reaction. So, and then that should be everything. Okay, so moving along, I just got to grab the other page. One other thing that's going to be a big thing on this is going to be the Lewis structures, being able to write Lewis structures. So in this case, what I ask you to do is to draw Lewis structures for the following, each one of these, and then state if resonance exists, show plausible resonance hybrids. So let's go through and just start doing them. So PBr3, phosphorus is going to bring 5 electrons to the party. Each bromine is going to bring 7. So that's going to be 21. So this is going to give us a total of 26 electrons. That's going to be, so we draw our skeletal structure. We get PBr, Br, and Br. So PBr3, so we're going to take away the 6, which is going to leave us 20 electrons. So we have to distribute 20 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. So that's going to be our structure. The next, so this is going to be complete. There is no resonance because none of the bonds can move. So that's the complete Lewis structure for PBr3. So the next one is going to be PO43 minus. So this guy is going to have 5 from the phosphorus. The oxygens are going to bring a total of 24 because each one of those is 6. And then we're going to have an additional 3. So this is going to be 32 electrons total. So we draw out our skeletal structure. We're going to have 8 from that, so that's going to give us 24 that we have to deal with. So we do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are our electrons. Now, if you left it like this, you would get partial credit, but you wouldn't get complete credit. Phosphorus can expand its octet, and we can reduce its formal charge by making double bonds. So in this case, the formal charge on this is going to be a -1, a -1, a -1, a -1. And then the phosphorus, if you do the formal charge calculation, you're going to get a +1. So in this case, we can actually, a better structure is we can make a double bond with one of the oxygens. And here you can see that now the formal charge is reduced. So it'll be 5 minus 5, giving you 0. This one will be a 0, and then there are your 3. So this is going to be a -3 charge. Now, here, this is a classic example of where you would get resonance, because this double bond could have been equally drawn on any one of those. So your resonance hybrids will look just like this. So you just move that double bond around to all of the different oxygen atoms. You kind of just go around in a circle. And that would be exactly what I was looking for. So drawing all 4 Lewis structures with the hybrid indicators in between, that indicates that you know there's resonance, and then you would be good to go. And you could just put a little extra that structure or whatever, just so that I know that these are the ones that you want me to look at, okay? Now, PBR5. So PBR5, we'll do the math over here so we have a little extra space. Typically on the exam I will give you more space, but on the practice exam I give you a little less. So PBR5, that is going to be 5 plus 7 times 5 is 35 for a total of 40 electrons. So I'm going to draw this guy out here. So if we draw our skeletal structure, we have now 10 electrons in the skeletal structure, so we take 10 away. That's going to leave us with 30. So we do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Everything is happy with the PBR5. All of our bromines have a 0 formal charge. Our phosphorus has a 0 formal charge. So that's what you're looking for. Now, IF4 minus. Okay, so this is a little bit of a tougher one. So IF4 minus, this is going to bring 35 electrons to the party plus 1 for the minus charge, so 36. We're going to have I and with 4 Fs. We're going to take away 8 electrons, which is going to give us 28 left over. So we put them in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I need to put in 2 more, so we're going to have 2 more there, and then that should be it. No resonance here because you can't make any double bonds move around. Checking formal charges, you'll see that the I has a -1 formal charge because it'll be 7 minus 4. Minus 4 is -1. Okay. So that gives you a flavor for what's going to happen with the Lewis structures. This is probably this question will be asked exactly the same way, just with different structures. Other things that could be on the exam might be I could give you a set of 2 different compounds that are similar, like CO2 versus CO3. Or like here, for example, PO4 3-. I could ask you what would the bond lengths be the same or different in each of the structures. So those would all be possible things that I could ask you. But pretty much, if you know how to draw the Lewis structures and you know about resonance and what that means, you should be good to go. Now the last one is a tough one. And I really like this question. I have to say, I think this question really shows if you understand lattice enthalpy, lattice enthalpy, and what's going on with lattice enthalpy and Hess's law, and the Bohr-Haber cycle. Because the reason why is because from this you have to do this all out of the air. This is basically something you just have to come up with on your own and put it together, just knowing the definitions for all the various things. Ionization energy, electron affinity, so on and so forth. So in this case, what this asks you to do is this asks you to show how to calculate the lattice energy of KBr using Hess's law. Write thermochemical equations for each step involved. And then the kicker is you have to indicate whether each one is going to be endothermic or exothermic. So delta H is a minus is going to be an exothermic process. Delta H is a positive is going to be an endothermic process. And then it says use the formation of KBr solid from the elements as your starting equation. So what I like to do is write up the lattice equation first, because that's what we have to do. So we know that the lattice energy equation is going to be KBr solid goes to K plus gas plus Br minus gas. So already you have to know what that equation is. So you have to know what the lattice energy equation is for KBr. You'd have to know what it is for any salt. So in this particular instance, that's where this is our target. So this is where we have to go. So the reason why I like to put this one first is because then we can start to for each sub-equation, we can decide whether we have to flip it or not flip it or whatever. We can kind of start to plug things in as we need it. So knowing this, it says, okay, so now we need to find this out. So now we're going to start with, it says to start with the formation of KBr from your starting equation. So what I'm going to do is I'm going to kind of flip back and forth between another page so that you can see how I'm thinking about this. So I need a second page to write down what the various equations are as we go along. So the definition for the equation for the formation of KBr is going to be the formation of KBr from its elements. So that's going to be K solid plus 1/2 Br2 liquid. Remember, these are the elements in their standard states. So you have to know this. These are the definitions that you have to know. That a formation equation, a heat of formation, is the combination of elements in their standard states to give the compound that you want. Okay? So when we plug this guy in, and the delta H of this one is going to be a negative. All heats of formation are negative for the most part. So when we plug this in, though, and I'm happy that if you want, what you can do is you can create two columns. A column where you put the one in. You basically can put a column that says, these are the ones that I'm working with, and then on the other one you put the column that you're going to have to cross everything out. So you show me all the crossouts in one column, in the other column you show me just what the definitions are. That's fine. Another thing you could do is just, sort of write out all of the different definitions like I'm doing, and then below it, write out all of the ones that you're going to do for the crossing. But the answer on the exam has to look like what I show you at the end. So in this case, we're going to have to flip this one, right? So in order to get KBr to be on the right side, the KBr has got to go over here so that it appears on this side. Okay, so KBr solid is going to go to K solid plus 1/2 Br2, and this is going to be a liquid. And because we flipped it, the delta H in this case is going to be a positive. Okay. Now, the idea here is for each subsequent step, we have to convert these now into K plus gas and Br minus gas. So in order to get this to all cancel out, we have to get rid of these and work our way toward K plus gas and Br minus gas. So let's take the potassium first. We'll just pick that one arbitrarily. So in order to go, one of the ones that we're going to need is to get this, we're going to have to get this into a gas, so that's going to be the sublimation. So that's going to be K solid goes to K gas. A sublimation is going to have a positive delta H by definition. And then we have to make K gas into the ion K plus. So the K solid is going to cancel, and then we're left with K gas. So now to get rid of K gas, we have to turn this into K plus, and the only way to do that is through a ionization. So K gas is going to go to K plus gas plus 1 electron. Delta H, in this case, because it's an ionization, we know that pulling an electron away is going to have to be a positive. Again, you have to know that all ionization energies have a positive enthalpy. So this is all part of the definitions that we taught you in both chapters 8 and chapter 9 and chapter 9 when we went over it. So now K gas is going to cancel. This puts us in good shape because now we're working our way toward K plus. So the next thing we have to do is deal with this Br2. For Br2, we have a 1/2 Br2. I'm sorry, we have Br2. So we're going to have to do Br2 goes to Br2 liquid. We have to get this into a gas, so we're going to have to do an evaporation. So that's going to be to Br2 gas. Now, you should note that in order for this to work out, you're going to have to put a 1/2 here and a 1/2 here. So you're going to have to half this on both sides. This goes for any stoichiometry. Because we're not dealing with numerical values for delta H, you could just put the 1/2s in and then still write just that delta H is going to be a positive. Remember, whenever you go from a liquid to a gas and you evaporate, that's an energy-intensive process. That's going to be a positive. So, but here you can deal with the 1/2 by basically what this would have been was 1/2 of your evaporation energy. And if you put 1/2 here, that's perfectly fine. It's fine. You could just put a positive, or you could put a 1/2. Both will get you credit. The important thing though is that you have to put a half on both sides, or a parenthesis and a half, in order to get full credit. So now the Br2 liquids will cancel out. And we've actually done this before. We've seen this in class, dealing with stoichiometry above, that we've had to use half equations for the bond breaking in this case. So now we have 1/2 Br2 gas. So the only step that's left is we can't have Br2. We have to go to Br. So if you remember, we're going to have to invoke a bond breaking, or basically a split of the diatomic. So in this case, we have our 1/2 Br2 goes to Br. Br2 gas goes to Br. And so this guy is basically the bond dissociation energy for Br2. So this is going to have a delta H that's going to be positive. Whenever you break a bond, that's what we're doing here. We're pulling the two atoms apart. That dissociation energy is going to be a positive. And our stoichiometry is going to work out here. So our 1/2 Br2 gases are going to cancel. And then we're left with Br gas. So now what we're going to do is we have to now deal with getting this into an ion. So we have to deal with getting this into a Br minus ion. So what we're going to do for this case is we're going to have to use the electron affinity. That's the only way. So remember the definition for electron affinity. I will show you. So the definition for electron affinity is you always start with the minus ion, and then you are going to steal an electron in the gas phase. You're going to steal an electron from that to form Br gas plus 1 electron. And this delta H is going to be a positive. This is the formal definition for electron affinity. But in our case, we're actually going to use the inverse of this. So you have to, I cannot stress enough that you have to memorize what an electron affinity is and the delta H for it. You have to be able to reproduce this on the exam. Because I guarantee you're going to see a question like this. So you have to know what an ionization is, what an electron affinity is, and all those good things. So in this case, we're going to have to flip this bad boy around, right? Because we have Br gas on this side, we want to go to Br minus. So when we write this down on our actual piece of paper, it's going to work out to be Br plus 1 electron gives Br minus. And because we flipped it around, that's going to give us a delta H that is negative. Okay? So on the exam paper, I need to see this, but you should know that this is actually the inverse of the electron affinity. Okay? I'm stressing this, that you have to know these, because I don't want there to be any surprises when you get to the exam. You have to know all of these different things. So Br gas, I should put it, is going to cancel. My electrons are going to cancel. So now we are left with, if we add everything up, KBr solid is going to, and this is a gas, is going to give us K plus gas plus Br minus gas. And if we were to add up all of these numbers here, we would get our delta H, which would be the sum of all of those numbers above. Okay? You don't have to write this on the exam per se, but you do have to show all of this. Okay? Now, a couple of hints. I really like this question for the reason that this shows that you understand everything that's going on, but you don't have to worry about any numbers. You don't have to do any math. It's just purely conceptual. But be prepared on the exam to deal with something like, for example, aluminum chloride. Or another one would be calcium chloride. So I've shown you what to do for a simple one, like potassium bromide, But at home, you should practice these two and see if you can do them. And if you can't, come visit me on Monday or come early before the exam and we'll go over it quickly. But these would be very good types of questions to put on the exam because I like this question very much, but you need to have a little bit of a challenge. I can't just give you NaCl. So dealing with a slightly different stoichiometry might be how we would handle that type of question. So this covers pretty much everything you need to know for the exam in general. There really isn't too much more. There was a couple of things that I didn't go over on this practice exam that you might want to know. A couple of things might be, there were a couple of very good questions in the homework about, like, for instance, if you had 1 mole of a photon, if you have 1 mole of a photon with a wavelength of 700 nanometers, how much energy would that represent, for example? So, for instance, how much energy would be imparted by 1 mole of a photon with a wavelength of 700 nanometers? There were a couple of these in the textbook problems. I actually did not put them into the practice exam just because the homework went over those quite a bit. But you should be prepared for something like this. This would be a good multiple choice question. Or for example, it could be a good open-ended question. So that's one thing that I didn't go over. I'm trying to think of what else. You should definitely look at the slides at the beginning of the slides. The beginning of the slides do a very good job of giving you a layout of what is on the exam, what is in the chapters. So that should be good. And I've given you a lot of homework problems for this. Those homework problems are very good indicators of what's going to be on the exam. A lot of these types of questions are in the homework problems. And for the multiple choice, the drill questions, which are in the content sections, those are all good things to look at, the drill questions too. So I can't stress enough for you to just look at everything that I've given you over the weekend. Make sure you can answer all of those questions and you'll be in good shape. And these questions on the practice exam. Okay, so with that, I will let you study. If you have any questions, certainly feel free to email me, or we can meet up the day or two before the exam. Thanks.